Hi there, people. So a lot of you have asked me how I read papers. And honestly, I don't think there is any super special method to it. But, I thought, because people have asked me to make a video on it, so I'll make a video on it. And I'll try to share my method of reading papers. And hopefully this is going to be somewhat of a mini series or a series where I every now and then discuss how I read one of the papers that I make videos about, and I'll try to select them such that different things are highlighted. Now I've selected this one right here for no particular reason other than I sort of remembered it, and I'm going to try to go with you through how I read this and how I encountered this, and kind of try to honestly share what I thought at the first time when I read it. And I hope this helps some of you. If it does help you, and if you like content like this, of course, feel free to share this out and subscribe. If you haven't seen my original video on this paper, it might be worth to go watch it. I'll link it. And with that, let's dive in. So, again, this might be not really something new, but I'll just go through it, okay? So first thing I do is, of course, read the title. So the title has three parts: end-to-end, object detection with transformers. So what I notice that I do myself is through reading a paper, it's like read the paper with an open mind. I don't do that. I almost immediately form an opinion and a hypothesis of what's going on. So I see transformers, so I know what transformers are. If you don't, I've made lots of videos on transformers. Attention is all you need is the base paper for that. So I know what a transformer is, okay. And I know that transformers are usually in NLP, are usually used in NLP. There are things like, other things with transformers, but it's usually an NLP model. Then I read object detection, and I know object detection is a computer vision task. So immediately this here is sort of a difference. And I immediately try to assess what's the new idea in this paper. And in this case, it might be, it might be applying transformers to object detection. But then I also see end-to-end. And the only reason to put that in a title is because that's the novelty. Because usually in deep learning, we're sort of used to systems being end-to-end. And even if most systems aren't end-to-end, a lot of people don't. It's like end-to-end image classification on ImageNet. Like, thanks. So I was guessing that the reason they put in end-to-end into the title was because that's actually something that's special about the model. So now I have two competing hypotheses of why this paper matters. First of all, because it does it with transformers, and second, because it does it end-to-end. And of course, the truth here is that the combination of end-to-end, transformers, all of that is what makes this model. And I already formed a hypothesis of whether I like this or not. I have to be honest. I have very quick judgment of papers of whether I like them or not, and then I sort of catch myself each time, and I still try to. So there, for most papers actually that I have sort of a negative opinion at the beginning, negative. There are papers where I think there is no way this is going to work or something like this. I'm actually positively convinced throughout the paper. So for most papers that I read, I'm trying to find the positive things in there, but I do form an opinion pretty quickly usually. All right. So the second thing, this part right here, I don't even see. This is like advertisements on Twitter. I have always had issues with author names. People will come to me and be like, have you seen the new Vinyals paper? And I have no clue. And then when they say that's where they use this character level model to do that, and I'm like, that paper. So I do not care who the authors are of a paper. I can't remember the papers by their author names. I've gotten better at it, I have to say, but I've always had trouble with this. Now, that's not to say that a name doesn't pop out to me. If this would be like Joshua Benjo or someone like really famous, then of course that would catch my eye. And but I also know that, you know, Joshua Benjo's lab is huge. So just because a big name is on the paper doesn't mean that the paper is going to be of any good or bad quality. Sometimes the authors give you an indication of what kind of research is there. Like if you see, I don't know, Jeff Clune or Kenneth O. Stanley, you know that there's going to be this certain type of learning to explore and kind of a bit more out of the box thinking in their papers, which I really like. But it doesn't immediately give you a clue. Maybe if you go by first authors, it's much more indicative if you have already read some of their papers, but most often I just ignore authors and go on. The affiliation sometimes matters in that it's a bit of a vicious cycle. If there's a big name affiliation like Facebook AI, Google AI, and so on, these papers also, they get more exposure in like the press and so on. So whenever Google AI publishes a paper, all of these pop sci magazines like The Verge and this and Life Hacker and Hacker News and whatnot, they like write a blurb about it. So often they get much more scrutinized for these papers. They get much more the public attention, but they also get much more scrutiny, which in turn means that there is a bit more pressure on them to do good experiments. So that biases me like a little bit into the direction of believing their experimental evidence more. Now, usually this is also backed up by the fact that I am actually convinced by their experiments, usually. So these big name papers, often I find myself, even without or disregarding the affiliation, to be convinced more than of like regular papers. My most often issue with papers is that I don't believe the experiments, and I make no difference. Like even if it's Facebook, my prior is the experiments are crap and I don't believe them, and they have to convince me of the opposite. But I can't say that it doesn't affect me that it's like a big name affiliation. Okay, so then the second thing is sometimes I see the paper on arXiv and I skim the abstract. Sometimes the abstract is informative and sometimes not. So here, this like blah, 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 a new method that views object detection as a direct set prediction problem. And I'm like, oh yeah, okay. It says streamlines the detection, effectively removing the need for many hand-designed components like non-maximum suppression, yada, yada, yada. The main ingredients called detection transformer, a set-based global loss that forces unique prediction via bipartite matching, and a transformer encoder-decoder architecture. So they make it clear here why it matters, and that's what I want to get at is sort of what's the new thing in this paper. Most papers are, even though they're all very long and have lots of math and so on, they often have like one or maybe two new core things that they really tell you. Sometimes zero. But a lot of times it's like one thing that they really do. And you sort of have to, but they're trying to cloak it often because they need to make their research as impactful as possible, right? But you need to sort of figure out what it is they're doing. Here they make it fairly easy for us in that they say, okay, they remove the need for many hand-designed components like non-maximum suppression, which tells me that they're building something that's easier than what came before them. And that already tells me it's not necessarily going to be better. Their argument is more that it's going to be easier, right? There are sort of two kinds of experimental results. The ones where you try to beat what came before you, and the ones where you're trying to say, look, our thing works just as well as this other thing while being more advantageous in some other metric. So I would place this already in the sort of second category. And then they say, what are the actual ingredients? It's a set-based global loss that forces unique predictions via bipartite matching. Now, at this point, I know what these terms mean, but at this point, I actually don't have to know what the terms mean. What I need to recognize is that I simply have to go later and figure out what that is. And a transformer-based encoder-decoder architecture, okay? So there are two things right here that I remember I need to pay attention to later. There's this loss, which seems to be special, and there is the transformer architecture, which they say, okay, that's the model basically consists of those two things. And then they have a short description of what it does. Given a fixed small set of learned object queries, Detter reasons about the relations of the objects and the global image context to directly output the final set of predicted in parallel. That almost tells me nothing. Yeah, okay, the model reasons. Maybe this in parallel is something, but the model is conceptually simple and does not require specialized library, unlike many other modern detectors. This sort of this enforces my hypothesis that they're going with the, hey, this is a much easier way of doing things approach. Detter demonstrates accuracy and runtime performance on par with well-established. That further confirms my hypothesis that this is on par, right? The runtime performance on par with the current state of the art. And at the end, they say, moreover, Detter can easily be generalized to proceed to produce panoptic segmentation in a unified manner. We show that it significantly outperforms competitive baselines. Training code and pre-trained models are available. Okay. Now this last part, when I first read it, is like, okay, can easily be generalized to produce this panoptic segmentation. This is, I didn't know yet whether this is like a central claim of their paper that it can do this segmentation, or whether this is like an added benefit to their paper, because you can read it in both ways, and I'm just ready to find this out in the paper. Now, after I've read the abstract and sort of already formed the hypothesis of what's going on. So here in my mind, I already sort of have a model of how would I do that, right? How would I do that? And then what would I do? So right now, what I might be thinking is, if I have a transformer over images that directly outputs the predictions in parallel, I'm imagining like an image, and the image somehow needs to go into a transformer. So maybe there's like an encoder, like a CNN encoder that gives me image features. And then so maybe you sample this down, this image. This is just me hypothesizing what could be going on, right? And then I might be unrolling that, right, this image into a vector of these lower pixels. And then, so in my mind, what I would do right here, without knowing anything more, would be to do something like BERT span prediction. So I would have BERT right here, and I would input this sequence right here, and then to detect an object, I would sort of think that maybe the BERT has an output that is the same length as the input, right? So it's very good at sequence tagging and things like this. So maybe how it detects an object is going to be that it sort of like tags the center location in the pixel of an object right here, or it tags somehow the corners of the bounding box. But then I don't know how this is going to be in parallel. Maybe BERT outputs like a score for each location, and then you do some kind of matching right here. So this is my initial hypothesis of what's going on. And then I scroll through, and honestly, the first thing I do is I go and find the pictures. And no different in all, like since your first book you read, that's what you do. I go and find the pictures, because usually if someone proposes anything new, that they're going to try to make a picture of it. Luckily, I don't do like super theoretical, whatnot, your Bayesian generalization bounds, and I don't know. So most often papers I read have some sort of picture, and that's very helpful to me. I know, but yeah. So I find this picture, and here I see, okay, you have image, you have CNN, okay, gives you set of image features, so far so good. Then transformer, encoder, decoder, then set of box predictions, so all of them come out here, and I already read there in parallel, and then bipartite matching loss. So here I can see they color these in different ways, and these color appear to match with these colors right here, right in the green here, and these, they also, this is a very good graphic, right? From this, I can already read that these here go to the no object. A lot of times, the graphics aren't very good. So this as well. I'm not saying in every paper you can learn by looking at the graphics. Like sometimes the graphics are terrible, and you're like, what's going on here? This makes no sense. This happens a lot. In this paper right here, this happens to be very, very good explanatory graphics. So I'll take advantage of that. And I do the same thing in the other papers, right? But then later, when it doesn't match what I read in the text, I'll have to, update my belief and so on. But here, I see that these go to no object, and this goes to no object. So I don't know yet that this is the test set. At the point where I read this, I was sort of confused by this, but I recognized that each of these boxes right here is going to be either resulting in a bounding box or in the no object prediction. So from that, I could conclude that these things here are maybe some sort of a fixed set, right? But I still thought that, that this would actually be the output of these image features, so that in this case you'd have like 6 set of image features, and then you'd have like BERT here. Even though that's not an encoder decoder, this was still my running hypothesis that somehow you'd map these image features to these boxes right here. So, and I didn't know what to make of this thing right here. So then I went through some more and look for more pictures. And they're not, sometimes I also kind of glance at the formulas, but okay, when I see this is just, this is kind of useless. Like, okay, cool, you minimize the loss, thanks. This, okay, didn't really pay attention to that. New picture, cool. So this picture is much more informative than the other picture. Now, I believe with the other picture, they were trying to showcase this loss, how they do the matching. And even though I could read a lot from that picture, I did not get that part. And therefore, I felt, when I saw this and I just glanced at it, I'm like, oh, wait, what's different than up here? It seems like the same, but okay. Let's look at this. So again, we see, okay, you have set of image features that comes out of the CNN. So that conforms with my belief. But then this here goes into a transformer encoder, and this comes out. So immediately I see, oh, this is not the same as these boxes here, right? That was my hypothesis, that these things here would be the colored boxes. So I say, okay, obviously that's not what happens. This thing here seems to be sort of the encoded image information. Then that's somehow fed into here, and that then there are these object query things, and they seem to correspond to this. So I'm a bit more confused right now. What I can see is that these then will result in these boxes. Okay. So being confused by that, I look for more pictures. So I go look for more pictures. This here seems to be like of a visualization. A lot of these papers have some sort of ablation experiments or so and so on. This I just find a really cool picture for now. I don't know yet what it means. This I don't know yet what it means. And I go down, skip all of this, and then back here in the appendix I find this here, which I immediately map to the previous, where this is the encoder and this is the decoder, and I've already read the attention is all you need paper, and at that point it clicked in me. It's like, this is not a BERT transformer, this is one of these transformers that has an encoder and a decoder, even though they told me like 50 billion times already. I was too stupid until this point. So now I know, okay, I see what's going on. So the image goes through here, and then this goes as a side input, like as an attention from the decoder to the encoder, like I know in NLP, right? So in NLP, this here would be a source sequence, like maybe if you do translation, and this here would be a target sequence. So now, whenever I see a transformer like this and it outputs something like this, I look at it as, okay, this here is sort of the input that goes as like a side input over here. And usually here you have the target sequence, but that's not the case right here, right? You have these object queries. So this is how far I get from the pictures. Now I go up. So I have I have questions now. I have questions. And that's when I start reading the paper. Only now do I start reading the paper. After I've looked through all the images, formed the hypothesis, and sort of have questions on how this works. And we'll go a bit faster from now on to just not bore you with all the things. So the introduction is often very important, even though it's called introduction. And maybe, if you read a book, like if there's like introduction or prologue or something like this, it's often kind of pointless. Introduction in these research papers is one of the most important points, because all of these papers, basically all of them try to convince a reviewer to accept them. And in order to do that, they will set up their main points and their main story immediately in the introduction. So what you'll usually have is a problem statement, which is here, like what's wrong right now. And then you have like a story of how their paper addresses the issue. Okay, and that's here. We streamline the training pipeline by viewing object prediction, yada, yada, yada. This is often formulates in words what the paper is about and what contribution the paper makes, right? This is like a longer abstract. The abstract is often very, very cryptic, very dense. This here is often much more informative of what the paper does. So for understanding the paper at a high level, the introduction is the best place. But given that I've already looked at the images and so on, I don't actually draw much new information from this thing. Then there's related work. And honestly, I skip it. Like, unless I'm the actual reviewer of a paper, like when I'm the reviewer of a paper, I read the related work. But often related work is just like, first of all, you cite a bunch of your friends, and then you cite the mandatory papers, and then you cite every single person that you think could be a reviewer or you've actually been rejected from a conference with a reviewer claiming that, you haven't compared or you haven't cited that or that paper. You can pretty much be sure that that's if it's not a glaring omission, if it's like a niche paper and you haven't cited it, then you're like, okay, I'm going to cite it just because the next conference you could be my reviewer again. So I'm not sure that these related work sections, they're necessary. Like if someone wants to write their thesis and they go and read this paper and they want references, oftentimes this is a good place, but a lot of it is just blah, 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 blah. Okay, I know. Disagree with me if you want. To reading quality. So at this point, I tend to not skim. So at first I skim, but at this point I tend to read every sentence and read it closely and understand it. And when I realize like I'm tired or something, I don't just skim the paper. I've tried to skim papers and it doesn't work. Try to read every sentence, understand every sentence. And okay, if you don't understand it, don't stop reading because of that. But try to not skim and be like, oh, yeah, okay, I got it. That is not helpful. Except related work. Skip completely. Cool. Then a lot of times in this paper now is the model. And this is the section I'm actually interested in, right? So I read very, very closely here, and then I find out what their loss is all about. And again, I stress, read these things and understand them, right? Sometimes it's hard, but if you're confused, that means either they've done a bad job or they made a mistake or that you haven't understood something. If you can't understand the sentence, try to read on. Maybe it's clarified later and then, go back. But again, do not like just start. A lot of times when I read paper previously, I wouldn't understand something quite well yet. And then I would be like, oh, yeah. And then I noticed that I'd start skipping and skimming more and more, because that would, pop up again and again, and I wouldn't understand it again and again. And then at the end, I would just be kind of glancing at the paper. And I don't want to do that right here. So I want to read every sentence and understand it. Okay, so here, then I find out about the loss. And then if I don't know something here, then I'll go and look it up maybe on Wikipedia or something like this. Now, I don't need to I don't need to understand every single part of it, right? Maybe I should correct myself. So for example, this bounding box loss here, they talk about the second part of the maximum cost of Hungarian post law is this box loss that scores bounding boxes. Unlike many detectors that do box prediction with some initial yada yada yada. They say the most commonly used L1 loss will have different scales for a small. So here they basically talk about how they mix the losses. They say overall our box loss is that defined as this and this. Now, I don't know what these losses are. I just assume there's some bounding box losses. So it's not true when I say understand everything. Understand the things that are integral to the story of the paper, right? How exactly they compute bounding box losses at this point, I don't care. I just assume that there's some loss that I can backpropagate, right? What is important is that they do this Hungarian matching thing, right? As soon as I get that, I'm like, that was this, this thing up here. This with the matching thing. Now I get it. Now I know, there are always the same amount of boxes here, and there are always the same amount of labels here, and all we need to do is somehow match them. And I immediately think, why is that relevant? Oh, because when something is already matched to an object, some other thing cannot be matched to the same object. And that's how we, prevent the fact that all the things predict the same thing, right? And so that immediately becomes clear. And as I said, there is usually like one or two ideas in a paper. I don't assume, or I don't care what their exact loss function is, because I've sort of gotten the idea up here of what the loss is about. All right, so I hope that's clear. Very closely read the things and understand the things that are necessary for the story. If you think something's not necessary for the story and then later end up not understanding, then maybe come back and read it again. In any case, I would rather skip something and assume it's not necessary if I think so, and then come back, than trying to understand everything. But the things I do read, I try to understand thoroughly. Okay. Then there's the architecture, okay, and that again I read closely and get backbone, okay, transformer, encoder, okay, and now I understand much more closely, decoder, okay, and here finally I get what this is about. Decodes n objects in parallel, yada yada yada. These input embeddings are learned positional encodings that we refer to as object queries, and similarly to the encoder, we add them to the input at each attention layer. So now I've already seen these object queries here, and the only word I actually need from this sentence are learned. The fact that they're positional encodings, I just kind of ignore. As soon as they say learned, I know, these things here are learned. They're always the same for each of the images. They're just overall learned. Okay, so now I feel I understand the entire model. And yeah, so they say auxiliary decoding losses, and these sometimes you have to pay attention to like auxiliary things, because those are the things that here they say explicitly, we found helpful to use auxiliary losses. Sometimes they won't say why they did it. They'll just say, our loss consists of 3 things. And, if you look at the 3 things, only one of the things is really a part of their story so far. And that you should immediately conclude that they've put in the other things because they tried it and it didn't work. Right? So you can also kind of get an estimate of the brittleness and so on of the system in that you see how many unnecessary things are there, or how many things are not straightforward, how many things aren't the easiest thing that you would do when you would go about and do what they did. Okay, so then this concludes this model or method. Usually the section is called like method or model or something like this, and you go to experiments. Now the main question I have so far, or maybe I have some more questions about the model itself that I haven't been able to pick up from this section, which is not the case here, but I simply keep those questions in mind and see whether they are resolved later, right? So I keep an awareness of what I don't understand. But from here on, my main issue is, are they demonstrating that their story works, right? So they're proposing a loss and a model. And in my mind, they now need to convince me that that works. And it's not as easy as simply to show me some numbers that they are good at some benchmark. They need to show me that they get those numbers because of what they claim. So here they claim, well, okay, they propose a new architecture. So what they need to convince me of is that the architecture itself makes sense, right? But in other papers, when you propose when you say like, oh, for example, in an LSTM, when you build in an attention mechanism and you claim, oh, the attention mechanism can look back at the source sequence in one step, then you need to convince me that that actually happens, right? So you need to, not only do you need to perform well, you need to convince me that you perform well because of what you claim your model does, right? So, and that's often difficult, and I specifically look out in the experiments for, usually the question is like, where are they trying to bullshit me, right? Where are they trying to, are they trying to bullshit me? Are they trying to cover up the fact that something doesn't work? Now, all the experiments are always in the best light possible, of course, and you have to keep that in mind. But a lot of times you can also already see from the experiments that, okay, are they doing something weird? Are they not showing me some obvious experiment? Or, and that's a lot of time the case, is there an easier explanation for why they get the results that they get other than their explanation, right? And it is their job to convince you that their explanation is the correct one for these numbers. And especially if there is an easier one that they haven't excluded, and then I don't believe the experiments if that's the case, right? If there is an easier explanation for the effect, I'm very skeptical. But some papers have an easier job here than other papers. So in this paper, they basically show results on a task, and since their paper is about, hey, our pipeline is just easier than other pipelines, what they first of all need to do is they just need to like match the numbers of other pipelines. And here I see that, okay, in these results, often you have maybe a table or something. Here you see like this, their model, other models, and their model is the best model in a lot of cases. Now, if the best thing is, of course, if their model throughout is the best. The worst thing is if it's like scattered like this. Even if their model is the best, but in every single benchmark, a different configuration of their model is the best, that's sort of a bad sign unless they can explicitly explain why that is. And it's also not that good of a sign if these things are spread out like this. Like sometimes this baseline is good, sometimes their model is better, and so on. So pay attention to that. Now, in this paper, it doesn't matter so much. That's actually fine, because what they're trying to show is that their model is on par and way easier. And they've already made the case in what way it is easier. It's easier in terms of architecture. If they were to say it's much faster, then after that I would expect, an experiment in speed while these numbers are matched. But since they say it's easier, I've already seen the architecture, I'm convinced of that. Now that they show, okay, our numbers match, or actually I'm surprised they even outperform a lot of times, then I'm quite happy with these experiments. So also look for differences between numbers and the spread of numbers. Now, it's not easy to say what if like 0.1 is a big or a small difference. That depends on the task. But if you know, pay attention to these things. Pay attention to the fact that these results are noisy, and oftentimes there is a lot more hyperparameter tuning going into the model of the paper than into the baseline models, right? You want to make your stuff look as good as possible. And here is a little bit where the institutional credibility of someone like Facebook comes in that I tend to believe their results a bit more than other results. Not mega, but a bit more. Yeah. Also look at patterns that they don't point out in the text. So if there is like a pattern, if you see like an interaction between the number of parameters and the score or something like this, just try to be on the lookout of that and see if you can spot something that you think or think about whether that makes sense or not in what your hypothesis would be. So here we go on, and okay, then they go into ablations, and a lot of these papers do ablations, and I generally appreciate that. So here they visualize that the attention mechanism in their model actually refers to different instances, right? Encoder self-attentions for a set of reference points. The encoder is able to separate individual instances, and you can see that pretty clearly right here, and even here with the overlapping cows. And this is the sort of experiment that I would expect that actually convinces me that their architecture does what it says that it does, right? And something like this, where you see like totally overlapping things with the attention of the individual things visualized. So telling me like, especially this one right here, the foot of the back elephant actually being focused by the attention of the bounding box of the back elephant. That's the sort of experiment that convinces me that their claims, like that their numbers really come from what they claim it comes from. Okay, so at the end of the experimental section, you should always ask yourself, have they really convinced me that their story is true, right? That the improvement, or whenever they get an improvement or whatever they get, is due to the story that they want to sell me? Or could there be like an easier explanation? Or does something not fit? Is like, are the experiments different than from what you would expect here? Okay, so these are my main questions. Are they convincing me of their story? It's not, do they have state-of-the-art numbers? I don't care. Even though, like, sometimes, so there is a bit of a catch. I don't care about state-of-the-art numbers. Now, let's say you have a table like this, and you have a computer vision model, and one of the models is like on the CFAR10 data set. Now, if your baseline model has like a 91, 92% accuracy on CFAR10, when I know the state-of-the-art is 96, I don't care, right? I know, like, I've done CFAR10, I know with like, I don't know, 5-6 layer CNN, you can reach these 91, 92, 93% accuracy. And to get to the 96, 97, you'd actually be like in the region of a wide ResNet and whatnot. I know that even though you're a few points behind state-of-the-art, I know, this is valid still, so I don't care. But if you were to be like at 80% accuracy on CFAR10, then I get a bit like, it's pretty easy to get to 90% plus with like a standard CNN. So there I immediately start to wonder, why? Is there an explanation? Now, this could be like a theoretical paper that says, oh, we investigate MLPs, and that's why we only get that number. So that would be fine. But if something is out of the ordinary like this, then I pay attention, but never because something isn't like the latest and greatest state of the art. That's just dumb, okay? And also, if only evaluate what the paper claims it does, right? If the paper says we want to show that we are on par with current models, then don't be mad if the paper doesn't outperform these models. They didn't claim that, right? So yeah. So after these ablations, I'm actually pretty happy right here with the results. And this right here, when I saw this, I didn't expect that, but I read the experiment description that these are these different learned object queries and what they do, and that gave me an increased understanding of how these object queries actually work, right? So at that point, I still had like a vague, I knew that these are learned, but reading this and sort of looking at it, studying it a bit, I was like, oh, okay, then I understood even better what they are. So again, when I say understand everything in the method section, you can still have questions, but you just have to keep it in mind for later. And then here I go on, and there's this DETR for panoptic segmentation, and they propose like a new model. So I first look at it and I'm like, okay, they propose a new model. They can do stuff like this. Now this is not object detection. And again, I'm not sure, is this like an add-on to the method, or was this up here just an intermediate step to this? And honestly, after reading that, I still wasn't sure. It seems like something in between. Of course, the paper is also a bit longer than other papers. It seems it's too long for just being a side note, but it's too short for being its own thing. So that was just a bit weird, and I treated it as just like we can also do this with our model. But I didn't pay like too much attention to that. Okay. So at the end, I look at conclusions. Now, the conclusions of a paper are much often, they are not nearly as informative as the introduction. The conclusions, they all often tend to be very generic and kind of hedging a bit against criticisms, saying what would be up for future work, which is again hedging against criticism. Because you simply say, well, we didn't do this, that's future work. So again, I read it, but I don't really pay attention to it. And then I gloss over the abstract. I just would kind of scroll through the abstract. If there's something that catches my eye, I would look at it, and if not, then not. And then I basically go to the start, and whenever I didn't understand something, I go back, I look at it again, and I try to think, are all my questions answered? And have they sufficiently convinced me that their story is the thing that really has the effect right here? And then if I now were to make a video of this, I've often found it useful to just put the paper away for a while. And I usually get the best result when I read the paper the day before and then make a video the day after. Or if not, I'll just, put it away, do something else, do some email responding, programming, going outside, eating lunch. Just some kind of a break between first read, or between first couple of reads, and I don't even think about the paper. I just kind of, it's just in the subconscious, it kind of brews, right? And I happen to think about the paper every now and then, but I don't make a conscious effort to be like, oh, how am I going to explain this and so on. But I just found the worst videos are the ones where I immediately make the video after reading a paper. And I've just discovered that if I kind of take a break and then I look at it again, right? I don't read it fully again, but if I have the feeling I've understood it, I don't read it fully again, but I just kind of look at it and go again through the story. And I think that's, even if you want to talk about a paper in a reading group or explain it to your friends or whatnot, this is often very useful. Just put it away for a while, let it mellow, and I find that helps a lot. Okay, that was my process of reading this particular paper. Now this is a high quality paper, so I find it's a pretty easy read in that I simply need to understand what they did and I'm pretty happy with their experiments. Maybe next time I can find an experiment or a paper where I'm initially more skeptical and not as happy with what I find. But yeah, let me know if you enjoyed this or if you would like to see any other explanation. I don't exactly know if this is what you expected from a video like this. So let me know. Maybe I have misunderstood you completely, or it's way too long, way too detailed, or way too undetailed. Yeah, leave me a comment and I'll see you next time. Bye-bye.